Hey, what's up, my chemistry people? Who is ready for some free response fun? I love free responses. Cylinder A has a movable piston and contains hydrogen gas, H2. An identical cylinder B contains methane gas, CH4. The diagram below represents these cylinders and the conditions of pressure, volume, and temperature of the gas in each cylinder. Part A. Is the total number of gas molecules in cylinder A greater than, less than, or equal to the total number of gas molecules in cylinder B? Justify your response. Alright, let's take a look at the diagram. Notice that the pressure conditions are the same, the volumes are the same, and the temperature conditions are the same. What does this mean in terms of the number of gas molecules in cylinder A versus cylinder B? The number of gas molecules in cylinder A is the same as the number of gas molecules in cylinder B. Boom. I've answered the question, but I have to justify my response. Boylin is a genius. Alright, that is true. But let's talk about how we can justify this mathematically. I come back to my good friend Pivnert, and I'm going to work through a calculation for cylinder A. I'm going to plug in my pressure, volume, and temperature values into the Pivnert equation. Boom. If I solve this for number of moles, 1.2 times 1.25 enter, divided by 0.0821 enter, divided by 2 95 enter. My number of moles of gas in cylinder A is 0.062 moles of hydrogen. Now notice, if I do that same calculation under the conditions for cylinder B, boom, my number of moles of methane gas is going to be the same. Boom! Now be careful, we're asked to compare number of molecules. So to be super clear for your grader, let's be sure to show the calculation to molecules. To do that, in each case, we're just going to take our number of moles and multiply it by Avogadro's number. Boom! So in each case, notice I have justified mathematically that I have the same number of molecules in each of my cylinders. And I don't know about you, but anytime I can get away with mathematical justification, winning. Subpart I. The balanced chemical equations describing the combustion of each of the gases are shown below. Will cylinder A produce a greater, a smaller, or an equal number of moles of water vapor after combustion than cylinder B? Justify your response. Assume the gases in each cylinder completely combust and that the volumes of water vapor are measured under the same temperature and pressure conditions. Alright, let's first do cylinder A. I know that in that cylinder I have 0.062 moles of hydrogen. Look at the equation that I'm given for the combustion of hydrogen. The relationship between water and hydrogen is a 2-to-2 relationship. So if I completely combust 0.062 moles of hydrogen, I'm going to get 0.062 moles of water. Cylinder B. Again, I'm starting with the same number of moles of gas, 0.062 moles of methane. Carefully consider the combustion equation that you provided. Here the relationship isn't 2-to-2, it's 2-to-1. So when I combust 0.062 moles of CH4, I'm going to make 0.12 moles of water vapor. So I'm going to make twice as much water vapor in cylinder B upon the combustion of 0.062 moles of methane than I would upon the combustion of the 0.062 moles of hydrogen. Don't forget to answer the question. Cylinder A will produce a smaller number of moles of water vapor after combustion than cylinder B. Boom. Answered, justified. Let's keep going. Part B. Is the average velocity of molecules in cylinder A greater than, less than, or equal to the average velocity of gas molecules in cylinder B? Justify your response. Alright, now this is a commonly missed question. Let's go back up and take a look at our two cylinders. Notice that the gases are at the same temperature. And recall that temperature is a measure of kinetic energy. And because they're at the same temperature, they have the same average kinetic energies. Now let's take a look at the formula for kinetic energy. Boom. Kinetic energy relates the mass and the velocity of the sample of gas. Notice that the kinetic energies can be the same. They can have the same temperature, but not necessarily the same velocities. Hydrogen, a gas with a very small mass, will be moving at a much higher velocity at a given temperature than methane gas, which has a much larger mass and moves at a much smaller velocity relative to the hydrogen gas. So, to answer this question, the average velocity of molecules in cylinder A is greater than the average velocity of gas molecules in cylinder B. Let's justify. Less massive gas molecules travel at a greater velocity than heavier gas molecules. Molar mass of H2 is 2.016 grams per mole. Molar mass of CH4 is 16.042 grams per mole. Boom! Part C. State a change in temperature and a change in pressure that would cause the gas in cylinder A to behave more like an ideal gas. Alright, this question is just asking you to recall under what conditions will a gas behave more like a gas? Increasing the temperature and decreasing the pressure will cause the gas to have more ideal behavior. Boom. Remember, if a gas gets too cold, if the kinetic energy decreases substantially, slows down, behaves more and more like a liquid, less like a gas. When you increase the pressure, you force those gas particles closer and closer together. So if we want an ideal gas, we want really hot temperatures and really low pressures. Finally, Part D. Show a numerical setup and calculate the volume of the gas in cylinder B at STP. Alright, now there are a couple different ways you can do this. I think the easiest way to do this is jump back up to Part A. Recall that we determined the number of moles in cylinder B to be 0.062 moles. When you're at STP, just take your number of moles and use the standard molar volume relationship that exists between moles and liters. 1 mole, 22.4 liters. 0.062 times 22.4. 2 sig figs, 1.4 liters of methane gas. Boom. And that does it for this vid. Have a fantastic day.